going to teach you a really important topic within lung physiology, West zones and VQ matching. West zones help us understand the VQ ratios within the lungs. V stands for ventilation and Q is for blood flow, and VQ ratio is how well these match. In an ideal world, you would get 1-to-1 matching. When we talk about VQ ratios, generally textbooks will describe that at the top of the lungs a VQ ratio of around 3, meaning 3-to-1. At the third rib, it would be 1 in an upright lung, and at the bottom of the lungs, it's about 0.6. West zones help us understand this. The three parameters we need to know is pressure alveoli, pressure arterial, pressure venous system. Within West Zone 1, the alveolar pressure is greater than arterial pressure, greater than venous pressure. This is because of the weight of the lungs and also the fact that a column of blood in upright lungs will have less pressure at the top compared to the bottom. Because of this, there's more ventilation into the alveoli than there is blood flow, meaning that you have a higher VQ ratio as represented here. In West Zone 2, you have more optimal matching, as arterial pressure is greater than alveolar pressure, greater than venous, meaning that the arterial side needs to pass the alveolar side to get to the venous side, so you'll have better VQ matching. In West Zone 3, you have arterial pressure greater than venous pressure, greater than alveolar pressure. Essentially, this describes the fact that the alveoli will likely be collapsed because of the weight of the lungs, and the weight of the blood down is higher, meaning that you'll get bypassed to the venous system. This essentially is a shunt. But then in other textbooks, it will describe a West Zone 4, and this takes into account the weight of the lungs, PI, which is the interstitium of the lungs. The arterial pressure is still greater than the interstitial pressure, which is greater than the venous pressure, but overall greater than the alveolar pressure, meaning that you bypass alveoli, and this is shunting as well. The way I remember the position of each of these is that I know that arterial pressure is always greater than venous pressure, and if you look at 1, 2, 3, 4, this describes the position of the alveolar pressure. First position, second position, third position, fourth position. In the lungs, we would likely want to have a VQ ratio of 1 for perfect VQ matching. However, as we can see here, this isn't true for the upright lung. If we want to figure out an average for, say, a 70 kilogram male, you would figure out your minute ventilation and your cardiac output per minute. So minute ventilation is respiratory rate times tidal volume minus dead space. Your average rest rate is about 12 at rest. Tidal volume in a 70 kilogram male is about 500 mil, and your dead space is about 150 mil. This means that your ventilation is about 4.2 liters per minute. Cardiac output is heart rate times stroke volume. Generally, it's quoted at 5 liters per minute for a 70 kilogram male. So if you simply take your ventilation, divide it by your blood flow or your cardiac output, which is 4.2 divided by 5, your VQ ratio generally in a 70 kilogram male is 0.84 across the entire lungs.